The introduction of integral control into a control system can reduce the steady-state error to zero. Integral control creates a restoring force that is proportional to the sum of all the past errors multiplied by time, as expressed in equation 11.4. Controller output due to integral control is proportional to the sum of all the past errors multiplied by the time they existed, modified by two constants relating to the proportional and integral control systems. For a constant value of error, the value of epsilon e delta t will increase with time, causing the restoring force to get larger and larger. Eventually, the restoring force will get large enough to overcome friction and move the control variable in a direction to eliminate the error. An analogy showing the power of integral control is a person who sits down in a comfortable chair to read a book. After a short time, the reader notices the dripping sound of a leaky faucet, a steady-state error. The first response of the reader is to do nothing, but as time goes on, the sink starts to fill up and spill over, which gets the reader's attention, and he or she gets up and turns it off. The point is that the dripping error was not increasing, but the effect of the steady-state error was increasing with time until finally the reader, the system, was motivated to do something about it. Let's look at an example. Consider the case where a robot arm has a steady-state error position of 2 degrees due to friction. This error is shown on the graph in figure A. As time elapses, the error remains at 2 degrees. Figure B shows how the restoring torque due to integral control increases with time. The magnitude of the restoring torque at any point in time is proportional to the area under the error curve. For example, after 2 seconds, the area under the error curve is 4 degrees seconds. Area equals 2 degrees times 2 seconds, as illustrated in figure A. Assuming that Kp is equal to 1 inch-ounce per degree and Ki is equal to 1 over S, then Kp Ki is equal to 1 inch-ounce divided by a degree second, and the restoring torque due to the integral control alone is 4 inch-ounces from figure B. After about 5 seconds, the restoring torque gets high enough to overcome friction and nudge the arm the last 2 degrees to remove the error. Once the error goes to 0, the area under the curve stops growing, so the torque stops increasing. However, it remains at the elevated level of 10 inch-ounces. This last point is important because it allows the gravity problem to be overcome, as previously discussed. The proportional feedback system of example 11.3, Kp of 10 inch-ounce per degree, has been modified to include integral feedback. The arm has been at rest at the 30-degree position when a weight is placed on the end of the arm, causing a downward torque of 40 inch-ounces, shown in figure A. Describe how the control system responds to the weight. So the solution: the proportional gain of this system was determined to be 10 inch-ounces per degree. As the following calculation shows, 40 inch-ounces of torque from the weight would cause the arm to sag 4 degrees. So output P is equal to Kpe. So E is equal to output P over Kp, or 40 inch-ounces divided by 10 ounces per degree, will give you a 4 degree sag, which is shown at time A in figure B. The proportional control initially provides the entire 40 inch-ounces of restoring force to support the arm, resulting in 4 degrees of error. Because there is an error, however, the integral control starts contributing to the restoring force. As time passes, the area under the curve increases, and the integral control provides more and more of the 40 inch-ounces needed to support the weight. while the proportional control provides less and less, as is shown in time B in figure B. Finally, at time C, the integral control is providing the entire 40-inch ounces and the error is 0. A new steady state has been reached. Integral control response can easily be observed on industrial robots. When a weight is placed on the arm, it will visibly sag and then restore itself to the original position. The integral constant Ki has traditionally been designated 1 over Ti and is referred to as repeats per minute or repeats per second. This is because if Ki is equal to 1, the integral contribution will increase by the amount of the proportional contribution every time period. If Ki is equal to 2, the integral contribution will increase by double the amount of the proportional contribution every time period, and so on. You can see this happening in the figure 11.5 attached. Recall that Kp is equal to 1 and Ki is equal to 1, and that the steady state error is 2 degrees, as is shown in figure A. Therefore, the contribution from proportional control alone would be 2 inch ounces, which has come from Kpe is equal to 1 times 2. Now, look at figure B and note that the integral contribution does indeed go up by the same amount of 2 inches ounce each time period. Although the addition of integral feedback eliminates the steady state error problem, it reduces the overall stability of the system. The problem occurs because integral feedback tends to make the system overshoot, which may lead to oscillations. One example of this problem is shown in the graphs. All mechanical systems have friction, and friction is nonlinear. That is, it takes more force to overcome friction when the object is at rest than it does to keep an object moving, a phenomenon which is referred to as stiction. At time is equal to 0, the system has just moved to a new position and stopped, leaving a steady state error. The restoring force is equal to the contribution from the proportional control plus the increasing force from the integral control. For a while, the object doesn't move, but finally the combined restoring force overcomes friction and the object breaks loose. Once moving, the friction force immediately drops, so some force is left over, which goes to accelerating the object. This may cause it to overshoot and the whole process starts again from the other side. The problem is that the proportional integral system has no way, other than friction, to slow the object before it gets to the new set point. The system must overshoot before any active braking will be applied. So unfortunately, the addition of integral feedback solves one problem, steady state error, but it creates others, overshoot and decreased stability. Also, the response of integral feedback is relatively slow because it takes a while for the error time area to build up.